All right, so in today's lesson, we're going to look at a couple of things. We're going to look at tree diagrams, and we're going to look at the general multiplication rule. There are actually two multiplication rules, just like there are two addition rules, one general and one specific. We're going to look at the general one today. So the lesson involves a real simple card game, the rules of which is that you start with 5 cards total, 2 aces, 3 kings. The player chooses their first card and records the results, and then chooses their second card and records the results. The player wins if they get either a pair of aces or a pair of kings. They end up with 2 cards that are the same rank. Now we're not going to play the game here. We're going to go ahead and just make the tree diagram, and then keep in mind that the start of the game for us is going to be 5 cards, so 2 aces, 3 kings. And we're going to fill in what is called a tree diagram. So here is your ace game here, and let's just say that the first card we're looking for is either an ace or a king. So if the first card is an ace, remember there's 2 out of 5. And we'll just call this event just the probability that the first is an ace. All right, the other outcome would be not getting an ace. So that would be a king. King and not an ace are the same thing. So that'll be 3 out of 5. And you notice that you either get an ace or you don't. And that's the entire sample space for just looking at aces on the first draw. So these add to 1. This and this. All right, so there's your first card with its probabilities. So we'll move to the second card. The second card is an ace, given that the first is an ace. Okay, now when you've pulled this card out, you don't put this card back. So if you have an ace, that card is out and you're only dealing now with 4 cards. Now you've already picked 1 ace, that leaves 1 ace left over. So this is the probability of the second is an ace. And remember that symbol means given that. The first was an ace. All right, so these are just the initial split. This column right here, this column right here is going to end up being all conditionals. Looking at this, your second card is an ace, given your first card an ace. The other option would be the second card is a king, given that the first is an ace. Now remember, you do only have 4 cards because you already picked one here. There are, however, 3 kings left over. Okay. Let's travel down this branch, and we've not completed this branch, but we've gotten as far as we need to on that branch, so we'll go down this branch. So let's just say your second card is an ace, given that the first card was a king. You picked a card, you got the king doesn't go back in, that leaves you 4 cards. And since you haven't picked an ace yet, there's still 2 sitting in those remaining 4 cards. So this is the probability that the second card is an ace, given that the first card is a king. And let's just say instead of going that way, we go this way. The second card is a king, given that the first is a king. We have 4 cards left over. Remember, we picked one here. And we picked one of the kings, so that leaves 2 kings left over. So this is the probability that the second card was a king, given that the first card was a king. Now, each one of these, this should total 1. Because given that you got an ace, you either get an ace or a king. That's it. So the total here equals 1. And then the total here equals 1. Same reason. All right, so if you know this one, then you can automatically subtract this from 1 to get the other one. And again, if you know this one, you automatically know this one. So let's go ahead and fill in the rest. This is going to be based on our general addition rule, which says that the probability of A and B equals the probability of A times the probability of B given that A happened. So we can go ahead and fill in these, because all you have to do is follow up along the branch and take whatever fractions are here for the initial split and the conditional and just multiply them. So this will be 2/5 times 1/4 is 2 out of 20. And that's the probability that you picked an ace and an ace. First is an ace and the second is an ace. We can get the next conditional. The next joint probability. These are all joint probabilities. So to get the probability that the first is an ace and the second is a king, that'll be 2/5 times 3/4. And that'll equal 6 out of 20. Following along, let's find the probability the first is a king and the second is an ace, and that follows this branch. So this will be 3/5 times 2/4, and that will be 6 out of 20. And then finally, the first is a king and the second is a king. That's the last branch in the tree. So that'll be 3/5 times 2/4, and again, that'll be 6 out of 20. So if we look at all of these joint probabilities, just like if we had them in a table, they should all add up to 1. So this is 2 out of 20 plus 6 is 8 out of 20, 14 out of 20. That'll give us 20 out of 20. So this will total 1. And the one thing that I have not put up here is that an ace and an ace is a winner, because they're both two of the same rank of cards. And then down here at the very bottom, a king and a king is also a winner. Now remember, there are two ways you can be a winner. You can be a winner with 2 aces. You can be a winner with 2 kings. So the next thing that we're supposed to find is to find the theoretical probability of winning the game. That would be an ace and an ace, or a king and a king. Remember, or means plus, and means multiply. So we can just grab this. That would be 2 out of 20 plus this outcome, which is 6 out of 20, which will give us 8 out of 20, or 0.40. So we know the probability of being a winner. It's not in your favor, this game. It really favors you losing in the long run, because we know the probability of winning is 0.4. Therefore, the probability of losing is 1 minus that, which would be 0.6. Okay, what's the probability that the first card was a king, given that the person won the game? Let's put this into symbols. This is the probability first is a king, given that person won. Okay, so we're asked for a conditional probability, and we're just going to rearrange this by dividing out the probability of A to both sides. So the probability of B given A is going to be, remember the both, probability of A and B over the probability of A. Remember, this is the condition. So let's go ahead and translate that into our events. This will be the probability of a king and winning, or king and 1, divided by the probability of winning, which is the probability that you won. All right, we know those things. King and 1 is this right here, because you got a king on the first and you won. So that will be 6 out of 20. That's just for the numerator. And then the probability that you won, we know that from here, right? That's going to be 8 out of 20. And we can just reduce those to decimals. That's 0.30, 0.40, which is 3/4, 0.75. So we're going to move on and look at our learning targets. The first learning target is to use the general multiplication rule, which is written right here. Probability of A and B equals the probability of A, and that actually should be times the probability of B given A. Learning target 2, use the tree diagram to model a chance process involving a sequence of outcomes. We've already done one example of a tree diagram. We're about to do another one. It will be pretty clear if I don't cram it into this little space. So we'll just go ahead and just mention to see the examples. And then finally, the third one is calculate conditional probability using tree diagrams. One thing that we need is, let me just get this color a little more closely aligned, is this. We use this on the very last thing on the front. The probability of B, given that A happens, is the both probability of A and B divided by the probability of A. And this is the event behind the symbol, is the probability on the bottom of the fraction. So if I have, for example, the probability, let's put this here, probability of A given B, it'll still be the joint probability, the same one, probability of A and B, but now this denominator will be this, probability of B. So it's a pretty easy formula. It's just a rearrangement of this formula. And we get a lot of questions asking for the conditional probability. Remember, that is the value that's in that center column in the tree diagram. Lesson app 4.5 is about lactose intolerance. That's the milk sugar causes digestive problems in certain people. It's common among people of African and Asian ancestry. In the United States, they've split things into some ethnic groups here, and these are not very precise ethnic groups. So there may be an ethnic group here that you're not a member of, but let's just pretend this is true. The 82% of the population is white, 14% is black, 4% is Asian. All right, that would be your initial split. They're just taking the population and breaking it into percentages by ethnicity. There is no given that. There is no, well, look at the next sentence. Moreover, 15% of the whites, 70% of the blacks, 90% of Asians are lactose intolerant. Those are conditional. So given that somebody is white, 15% are lactose intolerant. See how that can be conditional? So suppose we select a US person at random. So that's where we're going to start. We'll just write person. And we're going to do a split 3 ways. So up here, we'll have 0.82, and these would be for the part of the population that's white. 82% is white. Then we'll go this way, and we'll say 0.14. That's for the part of the population that's black. And finally, we'll do the 0.04, and that'll be for Asian. So there's your initial split. Okay, the next thing we're going to do is split each one of these into 2. And we'll just go ahead and say that of the whites, 0.15 is lactose intolerant. And I'm just going to abbreviate this, keep things simple. And then that would mean that 0.85 are not. And we'll do the same with both of these. For black people, that would be 0.70 are lactose intolerant. And that would mean 30% aren't. And for Asians, that would be 90% are lactose intolerant. And that means 10% are not. All right, so we have the initial split. These are all the conditionals. Now you notice I am not going into symbols or anything. I'm just writing these out in just basic language, and I'm trying to keep it simple so that we can, make sure that we have a good handle on this. All right, so let's look at number 2. Now there is another column of these numbers, and those would be all of your joint probabilities. Remember, all of these total 1, each one of these pairs total 1. Then we can get, this will be what, 8 total joint probabilities, and they will all total 1. But I'm not going to write them all out because I really don't need to. It says find the probability that a person is lactose intolerant. So I'm just going to not worry about the nots. So I'm only going to deal with people that are lactose intolerant. So going through this branch right here, to be white and lactose intolerant will be just 0.82 times 0.15. And I'm just going to put I'll just write this out. This will be white and lactose intolerant. We'll just abbreviate. And the product there is 0.123. That's these two numbers multiplied. I'm going to skip this because they're not asking about people who aren't, only the people that are. So following this branch, this will be 0.14 times 0.70. That'll be black and lactose intolerant. And that will be 0.098. And that's just that product here. And then finally, the Asian and lactose intolerant is 0.04 times 0.90. And that again will be Asian and lactose intolerant. And that will be 0.036. So there are 3 ways you can be lactose intolerant. You can be white and lactose intolerant, black and lactose intolerant, Asian and lactose intolerant. These 3 products here will not add up to 1 because there are 3 other ones, this one, and this one, that I just did not do. I didn't need to. If this question here had said, find the probability that a person chosen is not lactose intolerant, I would have then gone through the tree for these 3 joint probabilities and skipped the ones that I did. So find the probability that a person is lactose intolerant. It's just going to be the sum of these 3. So let's write this out. Probability of lactose intolerant, that's going to be 0.82 times 0.15 plus 0.14 times 0.70 plus 0.04 times 0.90. And when you add those up, you get a probability of 0.257, which we can write here, 0.257. So there's a 0.257 probability that a randomly selected U.S. person is lactose intolerant. So that's one of the kind of questions that you could be asked. So the last one, given that the person is lactose intolerant, what is the probability that he or she is Asian? So this is the probability of picking an Asian given that they're lactose intolerant, or a person is lactose intolerant. So we'll use that formula. That would be the probability of Asian and lactose intolerant divided by the probability of lactose intolerant. We know those numbers. Asian and lactose intolerant is this. So that'll be 0.036. And then the probability that a person is lactose intolerant would be that, 0.257. That becomes 0.1401. So there is a 0.1401 probability. Well, let's just read it from the beginning. Given that a randomly selected person is lactose intolerant, there's about a 14% probability, 0.1401, that the person is Asian. That's what we went over in section 4.5. So we'll see you for the next one.